Hello, I'm Jim, and I'm with the Material Science Engineering Department at Boise State University, and we're inside of the electron microscopy lab right now, and this is a scanning electron microscope, the SEM, one of the tools that we use to identify atomically and microscopically different things that are happening with materials.
And I'm Kelly. I'm studying material science here at Boise State University. I'm involved in student research. One of the really amazing tools that we have is the scanning electron microscope, and we have many other microscopes in other labs, but today we're going to be taking a look at what this particular instrument can do.
Let's take a look at steel under a scanning electron microscope. We'll start with this gear. I know, you're thinking, steel? Why? Well, there's a lot more than meets the eye. As we zoom into this broken tooth, on the right hand, we see shear planes where material has rapidly ripped off under the force of some machine that this gear was a part of. If we look past those, we get this grainy, textured surface, which is actually composed of many different crystals in the steel. The little white dots that you can see are specks of dust. If we zoom in even farther, we see a small gap start to appear. What could be inside? As we move closer, we begin to see another grain of material emerge. And this is a structure known as pearlite. You can just start to make it out now. Pearlite is very hard, but it's not very flexible. By tuning the amount of iron and carbon in steel and controlling the heating and cooling rates, we can get more or less pearlite in the steel that we make. So by understanding steel, we can control its properties. If we move in even closer and look inside this grain of pearlite, what we'll find is a regular repeating pattern. You can just start to see it now. In this pattern, each point is an individual atom, the smallest unit of matter. If steel were a material that had what's called a simple cubic structure, then it would have a pattern of atoms, and the basic unit of those atoms would occur in a cube. Looked at from the top down, we can see that we place this cube on top of the lattice, or the pattern of atoms, and that at each corner we have one atom occurring. By copying and pasting this cube many times, we build up a lattice, or a repeating set of points. And at each of these points, we have an atom. This is how all materials are made. Well, all crystalline materials, that is. Some things get a little more chaotic, and they could be in an amorphous state, or a liquid state, or a gas. But the materials we'll look at today are crystalline. If we zoom in even farther and look past this lattice and atoms, we can focus on an individual atom. Here, things are very different than the world that we experience, and they're governed by quantum mechanics. Beyond this point, we can't see anything else. And there you have simple steel gear. So you might be wondering why we spent so much time looking at steel. I mean, steel's been around a long time, and we thought we pretty much had everything figured out. If we could make steel stronger, or more lightweight, or cheaper, then interesting things would start to happen, because the global steel market is worth over $1 trillion per year. So if you can make steel stronger, you'll have everybody knocking on your door saying, "Shut up and take my money." And that's exactly what one Idaho scientist did when he was working at Idaho National Labs. Dr. Daniel Brannigan thought that steel was interesting enough to research. People probably told him he shouldn't, because everybody thought we had everything there was to know about steel figured out. But he ignored that and pressed on, and learned how to make nanostructured steel, making steel stronger and more lightweight. His company, NanoSteel, received a $150 million investment from General Motors. Because if you can make steel stronger and more lightweight, you don't need to use as much of it. So that does two things. It makes it cheaper, and it makes vehicles more efficient because they don't weigh as much. So if you make vehicles more efficient, then you don't have to burn as many fossil fuels. It means that driving doesn't contribute as much to climate change. So now you have some idea of why material science is really interesting to study, because you can take something ordinary and everyday, like steel, and you can make it better for everyone. And in doing that, you can make the world a better place, you can make it more sustainable, and you can make good money at the same time. In this video, we're going to talk about unit cells, planes, and directions. What we're going to look at in this video might seem really basic, but the basic things are really important because they allow you to create a foundation that lets you do really cool things later on. So just as an example, let's say you wanted to create the next Facebook or Snapchat, Twitter, or Google. You're probably thinking, I'm a high school student, there's no way I could do that. But all the people that created those companies were high school students at one point too, and a lot of them probably weren't even in AP Physics like you are. You're really smart, you can figure this stuff out if you work hard at it. Now, if you want to create any of these amazing technology products, you need to learn how to code. And at first, when you're learning how to code, it can be confusing, it can be difficult. It takes a lot of time and effort to really understand how to program well. And sometimes you lose sight of the bigger goal, which is creating some awesome service like Google that everybody loves. What you're going to learn today is kind of like learning the basics of how to code. The big difference between learning how to program and learning material science is that when you're programming, you're getting a computer to do what you want it to. When you're learning material science, you're learning how to program matter. And by programming matter, you can make all kinds of cool things. It doesn't end with steel. You can go to plastics. You can make computer chips. You can make solar panels that are so cheap that fossil fuels can't compete with them. And that's something that could really change the world. So let's jump in and start learning material science.
So this is just a quick description of the unit cell, and of course, well, the end product here is table salt, NaCl. And this is the unit cell for table salt. You've got the sodiums on the outside portion of the unit cell and the chlorines on the inside portion. As they're clustered together in their formation, in their lattice, you can determine the density through directions and planes. So we just got done talking about NaCl and how those atoms lie in a cubic unit cell. So let's take a look at a cubic unit cell. As you know, the measurements of each side are equal, therefore making it a cube, but also the angles, alpha, beta, and gamma, within the cube in the directions are also equal at each 90 degrees. So not all crystals are of this formation, but uniquely there are only 7 crystal formations. So we're going to go ahead and take a look at that now. So today we're just talking about cubic unit cells, but just to give you an example of what's out there, there are only 7 crystal systems. Basically they call them the Bravais lattice, but this encompasses crystals that have different lengths and sides and different angles, alpha, beta, and gamma. But that's pretty unique that we only have 7 crystal systems that encompass all things that we deal with. And without a knowledge of crystal systems, we wouldn't have things like our laptops and computers and Facebook and Snapchat. So it's pretty interesting. Okay, we just came from defining the unit cell. Now we need a way to describe directions and be able to convey those understandings to other people. So the best way to do it is to have a 3D image of a cube and then define the axis. So the first point is you want to find a point of origin. So we'll call this point right here, point 0, 0, 0. And that is your point of origin. And then if you draw a line down this particular vector, we'll call that point X. In the previous video, I think it was called A, but just for our illustration here, we'll call that X, and we'll call this point, or this direction vector, Y. And then the direction in this vector we'll call Z. So as you are labeling directions, you have your X, Y, and Z. And so that would be associated with these particular points from the origin I've labeled X, Y, and Z. So for instance, we were supposed to take a measurement. You know a cube is equal on all sides. So at this particular point right here, this is X equals 1. So if you were to do a direction, then you would label it 1, 0, 0. And that defines this particular point right here. And if you were perhaps to want to identify the corner of the cube in the Y direction, this particular point right here, you would put a direction indicating 0, 1, 0. And then the same would apply for a direction point in the Z direction. It would correspond to point location 0, 0, 1.
Okay, so now that we know what a unit cell is and we have a little bit of background on crystalline materials, we can learn how to navigate within that space. So here we have a cubic unit cell shown in gray, and this is a 1-1-1 plane. And so a 1-1-1 plane is specified in this format where you have your X, your Y, and your Z values. And a value of 1 in any of these locations means that we move from the origin, which is typically placed here at the corner, although you can move it to your preference, and we move out 1 full length of the unit cell in X for a 1, move out 1 full length in Y for a Y, we move 1 full length in Z for this Z coordinate. And when we connect each of those points, we have the 1